Hello, my name is Spencer Negri, and Dylan and Hari and I worked on an introduction to ElasticSearch. So to start things off, I'll talk about a very brief history of development. It was first created by Shay Bannon. In the first iteration of Elasticsearch, it was known as Compass, although it had relatively the same goal, just less features at the time, and obviously more issues. So during this iteration, Bannon was really going for to use his words, a scalable search solution. I'll talk about why he wanted to create a Compass and Elastic later, but it was really based on the basic idea that he wanted to be able to search large chunks of data very quickly, very efficiently, and and essentially that. It was written in Java. And Elasticsearch was released finally in 2010 as version 1.0. It's now in version 5.0 in 2018, and yes. So more on the history of Elasticsearch. This is just a simple timeline of how it happened. So in 2012, the company was actually formed as Elasticsearch, and then 2014 is when they came out with their 1.0 release. 2015 is when they actually became known as Elastic, and 2016 is when they're in 5.0, and in 2018, like I said before, we are in version 5 still. So now I'm going to talk about why Shay Bannon created Elastic. So when Shay was living in London, he was working to become a developer, and his wife was training to become a chef, and she was constantly learning all of these new recipes, and she was trying to basically catalog them and store them somewhere so that she could figure out she could basically search them easily and look them up very easily. So Bannon decided to create an app that would allow her to quote him, capture all the cooking knowledge she was gathering during her chef lessons. He wanted her to be able to search her cooking knowledge base and come out with a recipe and have it be very quick and easy process. But the core idea behind it was the fact that he wanted you to be able to type in like a singular thing and access data based on that singular thing. So in this specific example, he's talking about he wanted her to be able to type in an ingredient, for example, and an ingredient would unlock all of these recipes, which essentially became the core feature of Elasticsearch with indexing and stuff like that, but we'll talk about that later. So because of this desire essentially to index things and have every single thing within a database mean something for searching, he was drawn to Lucene, which is essentially just an indexer, basically speaking. So Compass was created on top of Lucene, but it was really created because he wanted to simplify Lucene for Java applications too. So he started really working with Lucene, and that's where he got pointed towards Elasticsearch because, Lucene and Elasticsearch go hand in hand. He started developing very specific functions for Lucene, and eventually it came to be known as Compass. And then once he had created Compass, people in the community started using Compass in ways that he didn't even imagine it could be used for. And this is kind of what made Compass so popular, is he was able to work with these people who were helping him progress and helping Compass progress by using it in unique ways, and it just really started to get noticed within the community. So yes. So another key feature of how Elasticsearch was developed was I believe these people were living in San Francisco at the time. But Logstash and Kibana were being developed literally at the same time as Elasticsearch. They were going hand in hand. In fact, all of their 1.0 versions released on the same exact day, which was absolutely on purpose because they were so key to each other. Dylan will talk about Logstash and Kibana later, but just generally, Logstash is a log ingestion tool, and Kibana is a UI data visualization tool. So they were basically very much going hand in hand. Bannon was developing a search engine that could be used for analytics, development. With analytics goes visualization. Obviously, you need a way to interpret what you've produced. So that's where Kibana comes in. Log ingestion, the log ingestion tool, Logstash, is very important because even today, one of the main uses of the Elasticsearch is doing is analyzing logs for various things like monitoring, development, for performance, which I will talk about later. But yes, these three companies were going hand in hand in development, and they were growing off of each other. They were debugging issues together, and they eventually became known as the Elk Stack. So an interesting problem that they actually ran into during development, which I thought was very interesting, is, and this is a direct quote from Shay Bannon, which I won't actually read, but as you can see, they had a lot of versioning problems. They were having issues where very specific versions of each of their softwares would only interact with very specific versions of their other software, so of other pieces of software. So just to quote him a little bit here, he goes, and if you're using Elastic 1.5.2, that's only compatible with Kibana 4.0.x, Logstash 1.4, etc., etc. And I just thought this was very interesting because he also said that no amount of matrix could solve this issue. So I think this was a really key point in development. They wanted to make it complete, all of their versions completely universal and interact perfectly with everything, which really became a very crucial part of their product later, because one of the strong suits of Elasticsearch is that it's seamlessly able to interact with other plugins, which makes it such an amazing product. So yes. So now moving on to Lucene, I'll give you a brief overview of what Lucene actually is. Lucene is simply an indexer. Very generally speaking, it assigns indexes to certain pieces of data, which will be very important to making Elasticsearch successful later, which Dylan and Hari will talk about. But essentially, this was the core part of his idea when he was developing the recipe app. He wanted you to be able to type in an ingredient and be indexed in such a way that if I type in an ingredient, it brings me to a multitude of recipes using that ingredient, for example, or it opens up new recipes that use that ingredient, stuff like that. So anyways, back to Lucene. It's created by Doug Cutting in 1999. The initial goal of it was to make SQL databases more easily searchable. As a lot of us know, most SQL databases are not indexed. You can have MySQL databases that are indexed, which actually makes them a lot faster. But essentially, in the early 2000s, especially with the lack of, or the difference in hardware that we have today versus the early 2000s, speed was obviously a very large concern of businesses trying to do analytics on database using data in their databases, and they were very large, and hardware was slow, so it was very dependent on software to optimize these things. So Lucene was created out of this desire to make searching databases much easier and much quicker. So these are just a few questions that Lucene tries to answer that the creators were considering when they were developing Lucene, just to give you an idea of how Lucene actually works, what it tries to achieve. So the first one is, how do we support queries that normal users will actually type? This is like a very basic concern of Lucene. They essentially just wanted people to be able to type in their own queries. And they wanted to match the people's desire for which queries they wanted, and have support for those, obviously. How do we rapidly search all the data we have in one fell swoop? So this obviously goes back to what I was saying with the SQL databases being slow. Lucene's main focus was to speed up searching. So yes. how do we order results when there is more than one likely match? This is a consideration of every search engine. It's very important how we present data to people analyzing it. It's very important to the outcome of the analyzation of the data. Lucine was curious about how, how do we basically decide which search result pertains more to a query, which is a fundamental part of search engine. And lastly, how do we summarize the full result set even if we only have enough space to display part of the set? So, especially when you're dealing with extremely large data sets, it's very important to prioritize certain things, which goes back to the last question. And if you don't have enough space to display everything, how do we describe the entire data set to the user, which is another very important part of a search engine. So moving on to the problem that Elastic solves, it's essentially the same as the problems that Lucine tried to solve. We don't currently have a way to search databases quickly. SQL databases are notorious. I'll talk about this later, but SQL databases are not very good at full text searches. So for example, just to give you a brief explanation, Elastic, for example, will index things and will allow you to go directly to your search result, versus SQL databases generally have to scan all rows and columns for your match, essentially. Then the last thing Elastic needed to consider was we need it to be scalable. We want to use this on a very large scale. We know how large people's databases are. We know how sparse they can be. We know how many systems they have. We need it to be applicable to very large and sparse systems, and we need it to be easily applicable to these things. So now I'll talk about just a little bit about why SQL is slow compared to Elastic, which Dylan and Hari will get into later. But basically, as I said before, SQL needs to search an entire row, column, or whatever it's looking for. It's basically, SQL databases can be indexed, which makes them very quick. Certain rows and columns are marked as having certain things, for example, so it'll be indexed accordingly, and then when you search for it, it will go straight to that row or that column to look for that thing, which makes it very, very fast. This is essentially the idea behind Elastic, which is why it makes it faster. Everything is indexed. You can say, I have a key and I'm searching for a key, and I know where that key is, so I can go directly to the value associated with that key, which is why it makes it so fast. And this was the driving force behind the creation of Elastic, is we need something faster than SQL because we have such large databases. So just a little bit more on what problem does it solve. We need a user to deal with huge amounts of data. We need it to be scalable. And he really wanted it to work with Logstash. So these are just kind of, and then simply speaking, we want it to be very quick. So these are kind of just some things to consider that Elastic would solve. So the solution is speed. ElasticSearch can be about 10 times faster than a SQL query on the same hardware, which is a very significant difference in time. So it's it can be a lot faster than SQL. One of the reasons for this also is indexing, and it uses its own querying language, which Dylan will talk more about as well. But basically, ElasticSearch is a document store based on JSON data. So, and the querying language is also based on JSON. So obviously results are scored based on how close they match the query. Another thing that makes it fast is you can basically filter out certain results that you don't even want to consider, which makes it a lot faster. And the other main reason is it's not constrained by things like rows, fields, and columns. It's just a document store. So all the data is stored as JSON objects with keys and values. So there's no essentially like parsing through tables and rows and stuff like that. It's mainly just you're looking for an individual key within a document, which makes it a lot faster. So the other solution is scalability. And I say allows for horizontal scalability, i.e. the addition of new nodes and machines. So horizontal scalability is the idea that if I'm running Elasticsearch locally on my computer, and I'm using my computer as a node, I should be able to add another computer um, as another node, as another computing node. Vertical scalability has more to do with upgrading your current computer, um, but Elasticsearch is great for horizontal scalability. It's very easy, which, as I keep saying, Dylan and Hari will get into later, but it basically divides the work among the nodes. It's very easy to set it up on a new node. Um, it basically uses shards of indices divided on all of these nodes, so each node only has a certain amount of the search work um, to take on. So, but this is kind of Elasticsearch's main point of selling is, and why it's so popular among these like huge companies like Sprint and Netflix, is because they have all this data coming in every second, and they have all these machines that are gathering this data, and they needed a solution that was able to fit and be easily scalable if they're growing so quickly to all these machines. So just to go over some very general use cases. So Elasticsearch is extremely proficient at searching text databases. So one of the things that it's very useful for is obviously log searching and log analyzation. Many companies use this for monitoring, which we'll get into later. But the most important point about this is that I'll give a quick example of Sprint. They have many documents coming in at one time, many records, many logs coming in every second. Not only do they need to store them, they need someone in sales to come in and look at, well, certain people are buying in these areas, whatever the sales person needs to know. They need to be able to search the data for certain aspects. They need to be able to visualize it. They need to be able to analyze, all so that they can analyze it, excuse me. And this is what Elasticsearch allows them to do, is it allows them to scale up to thousands of machines, search data very easily, and output it very easily and in an intelligent way so that people can look at it, increase sales, do whatever else Sprint needs them to do. So this brings me to my last point about Elastic, which is the industry impact of Elastic, which frankly, after doing research on Elasticsearch, has been very large, and one can even see that without doing research. It's very obvious that a company who is able to analyze such large amounts of data is going to be able to do something with that data and use it in an intelligent way. That's most of where things are heading towards nowadays with machine learning, AI, things like that. It's all dependent on data, and especially the more data you have, the more data you can analyze. Generally, the better the outcome. It obviously depends on the quality of the data, but generally speaking, more data is better. And some of these companies have so much data they don't know what to do with. Sprint says they get 3 billion records a day, which is a crazy number of records. They're constantly taking in data, and without Elasticsearch, there's no way that they could analyze all of this. They can store it, but it's just simply too large, and it would take too long to be able to search through this data to do analytics on it. It's also very important because on top of this, which goes back to scalability, now a company who has thousands of machines and monitoring all of those machines is very difficult because all of those machines is outputting some number of log files every whatever time frame you want. When you multiply that by all the machines in a system, especially if there's an error happening, they're going to be outputting more than normal. Gathering all these log files and searching them is very difficult, and it's very important because a company wants to figure out what's going on in the log files. Are there common issues? Are there common elements? How can we fix these issues? But it's overwhelming, and they need it done as soon as possible, so that they can get the system back up. With old databases, it's not possible. It takes too long, and that's where Elasticsearch comes in. It's a very important aspect for the companies trying to manage very large and spread out systems, and progress using their large data stores.
till now is what is Elasticsearch, why it is used, and some of the basic terminologies that are being used in Elasticsearch. Now let us see a little bit about the Elasticsearch architecture. As like any other distributed system, Elasticsearch consists of multiple nodes. Each node is nothing but it's just a running instance of Elasticsearch, and there will be a lot of Elasticsearch indexes within each node, and there will be a lot of shards within each indexes. We'll see what are these in the upcoming slides. As of now, just have this black box idea. And as we already know, Elasticsearch is highly scalable, and the nodes can be added and removed at any point of time, and the cluster actually reorganizes itself to distribute the data equally. This is taken care of Elasticsearch, and we don't need to do anything on our part. If you take a Elasticsearch cluster, there is a master node which is in charge of managing the cluster-wide changes like creating or deleting an index or adding or removing nodes from the cluster and things like that. Master node is also will also take part in the search part. I'll talk about it in a bit. And the data is actually stored in the data nodes. There are many varieties of data nodes such as ingest nodes, ML nodes, and based on each operation, each one is actually preferred. Users can talk to any node in the cluster, I mean query any node in the cluster, including the master node, and every node knows where each document lives and can forward our request directly to those nodes which hold that particular data. Whichever node we talk will change into a coordinating node, and which will manage the entire process of gathering the response from the nodes and holding the data and returning to the client. As I already said, everything is managed by Elasticsearch, and we don't need to configure anything particularly in the application layer. Elasticsearch nodes consist of multiple Elasticsearch indexes, which in turn consist of multiple shards. Index is nothing but a logical namespace. It's more like a name given to a collection of similar documents. Shard is a container of data. Shards are how the Elasticsearch actually distributes the data around the cluster. Documents and the indexes are actually stored in the shards. As the cluster grows all the strings, Elasticsearch will automatically migrate the shards between the nodes so that the cluster remains balanced. A shard is actually a Lucene index on top of which the Elasticsearch works. A shard can either be a primary shard or a replica shard. Each document in an index will actually belong to only one particular primary shard. At any given point of time, a document can never be present in more than one primary shards. The read requests can be accessed or can be processed by the replica shard or the primary shard, but a write or update request can only be processed by the primary shard, and once it is processed, the primary shard gives separate commands to the replica shards to update the documents. As you can see from the image, the replica shards and the primary shards can be present in any of the nodes in the cluster, but the Elasticsearch maintains the structure in such a way that primary shard and the replica shard doesn't belong in one single node. Elasticsearch is highly scalable, and one of the main reasons for this is sharding. Sharding helps us to solve two main problems. It allows us to store large amounts of data, and it increases the performance of the Elasticsearch by reducing the search space. Imagine you have 1 TB of data, and all your physical machines have a limit of 500 GB. At this point, no single machine can store the entire data, and we have to use sharding to solve this. In sharding, large indexes are divided into small indexes, and all these indexes can then be efficiently stored in the cluster of nodes. By dividing the data into smaller chunks, the search space is also reduced. Instead of searching one document in 1 TB of data by one single machine, now the data is divided into 250 GB of data across the cluster, and all the nodes just have to check for that one single document in their own 256 GB of data. This increases the performance. One main problem of sharding in Elasticsearch is the number of for an index can only be given at at the time of creation of the index, and it cannot be changed after that. This is because Elasticsearch uses a hash function to map the document to its original location in the cluster, and the hash function depends mainly on the number of shards. By changing the number of shards, we mess with the hash function, and then we might not be able to correctly locate the document in the cluster. If at all we need to change the number of shards in the future, the only way is to create a new index and move all our data from the old one to the new index. But chances of this happening will be is minimum, because even a index with a shard size of 5 will be able to store at least 500,000 of documents without any issues. Hardwares are bound to fail. The more the number of machines in the cluster, the higher the chances of the machines going down. It is always better to have some kind of fault tolerance or a failover mechanism, so that even if one or two machines go down, the system is still available and there is no data loss. Replication is mainly done to solve these issues. Elasticsearch natively supports replication of the shards. Replicated shards are called replica shards. Replication actually serves two main purposes. The one being being able to provide high availability in case node fails, and the another one being an increased performance. For replication to even be effective, if something goes wrong, replica shards are never allocated on the same node as the primary shards, this means that even if an entire node fails, you will have at least one replica of all the primary shards of that particular node. The other purpose, as I mentioned, is increased performance. This is the case because searches can be executed on all replicas in parallel, meaning that replicas are actually part of the cluster's searching capabilities. Replicas are therefore not exclusively used for availability purposes, although that is often the primary motivation. As like shards, the number of replicas can also be defined while creating an index. The default number of replica is 1, which is like being one for each shard. This means that by default, a cluster consisting of more than one node will have 5 primary shards and 5 replicas, totaling 10 shards per index. This Now let us see what happens when the Elastic cluster receives a create or a delete command. The receiving node actually takes the document ID and finds the node which has the primary shard of the required document. It then forwards the process to the particular node. The delete or the create command is then performed on the primary shard. Once the once the operation is successful in the primary shard then sends parallel commands to all the replica nodes, replica shards to update their corresponding documents. Once the primary shards and the replica shards return success, it is then forwarded to the coordinating node, and then the coordinating node returns the status to the client. The default consistency in Elasticsearch is quorum level consistency. Elasticsearch actually waits until a majority of the shards are available before it starts a write or delete operation. In this example, the client actually sends a create or a delete request to the node 1. The node 1 then uses the document ID to determine that the document actually belongs to P0 shard. It then forwards the request to node 3, which actually has the primary 0 shard. The node 3 then executes this request on the primary shard. Once it is successful, it then sends parallel request to node 1 and node 2, which actually has the replica shards. Once it is successful in the replica shards, it returns access to the primary shard. The primary shard then returns access to the coordinating node, which is the node 1 in our case. The node 1 then returns access to the client. Let's see what happens when we want to get a document from the Elastic cluster. The client sends the GET request to any one of the nodes in the cluster. Then this node then becomes a coordinating node and uses the document ID to find all the nodes which has the primary as a replica shard of this document. It then selects any one of those nodes and forwards this request to that particular node. This node then fetches the document from its shard and then sends it back to the coordinating node. The coordinating node then gets the document and sends it to the client. Note the point here that the request can be transferred to either the node which contains a replica shard or to the node which contains the primary shard. It doesn't matter here, and this happens in a round robin fashion so that the traffic is balanced. In our example here, the client sends a GET request to the node 1. The node 1 then uses the document ID and finds that the document actually resides in the 0th shard. The shard 0 actually resides in all three nodes in the cluster, but in this case, the node 1 reroutes this request to node 2, which contains the replica shard of the 0th shard. Node 2 then gets this document and sends it back to the node 1. Node 1 then sends it to the client. We saw how Elasticsearch handles create, delete, update, and get requests from the clients. Now let us see what happens when a search is executed on the Elastic cluster. A search request is executed in two phases, namely the query phase and the fetch phase by the Elasticsearch. In query phase, the actual query is broadcast to at least one copy of all the shards in the index. Each shard executes this search locally and builds a priority queue of matching documents. A priority queue is just a sorted list that holds the top n matching documents. The size of the queue depends upon two parameters, namely from and size. The size of the priority queue will be equal to sum of both the parameters from and size. All the shards formulate their priority queue. It then sends those priority queues to the coordinating node. The coordinating node then combines this all locally sorted priority queues into one single queue. In our example, the client sends the search request to node 3, which creates a priority queue of size of both sum of the both parameters from and size. The node 3 then sends the request to node 1 and node 2, which has the shards 0 and 1. Note the point here that the request can be sent to either a replica or the primary shard. It doesn't matter here. The nodes then form their own priority queues, which is locally sorted, and sends back those sorted priority queues back to the node 3. The node 3 then forms the globally sorted priority queue. Now this priority queue consists of all the document IDs which match the search request. Now the documents corresponding to these document IDs has to be fetched and returned to the user. This happens in the fetch phase. The fetch phase is similar to the document retrieval that we discussed earlier, but the only difference here is instead of one single get, we issue a multi-get and return all the documents from the result of those commands. In our example, once the node 3 gets all the document IDs that matches the search request, it issues a multi-get command to all the nodes which contains those documents. The nodes then fetches the document and returns it back to the node 3. The coordinating node, which is the node 3 here, then returns these documents to the user. Till now we saw how the Elasticsearch manages all the CRUD requests and how the search request is handled by the Elasticsearch. We also saw a bit about the Elasticsearch architecture. Here are a few tips that will be helpful while creating an Elastic cluster. Each update in Elasticsearch is actually a delete command followed by a create command. Thus, we should avoid constant updation of documents. Shards can't be split, and so we have to be careful while assigning the shard size while creating an index. As we can't split a shard, people tend to overallocate the number of shards. This will be a problem because for each search, the Elasticsearch has to search all the shards for a given index and then return the result. This More number of shards means the time taken to formulate the resultant documents will be more. Thus, overlocating the shards will become a problem. It's always advisable to store relevant documents together using an index or a type. Even though Elasticsearch can handle multiple volumes of documents, it is primarily a search engine than a DB. Thus, we have to formulate our queries in such a way that we don't return too much documents. Elasticsearch allows us to configure a lot of parameters, but this doesn't mean that we have to configure those parameters. The default settings provided by the Elasticsearch is fairly good, and working on with those itself will provide us fairly good results. To sum up, Elasticsearch is a distributed search engine which uses Lucene, an advanced high-performance search engine library. Elasticsearch is highly scalable and it can be scaled to hundreds of servers and can operate on petabytes of data. It supports multi-tenancy and can serve multiple requests simultaneously. As discussed earlier, Elasticsearch is highly configurable. Right from the number of shards to the way in which the request should be routed, everything is configurable in Elasticsearch. But as said before, default setting is always fine when working with Elasticsearch. The Elasticsearch has some good conflict management tools. It has version numbers to track the versions of the documents, and by this it can resolve updates and search conflicts.
Hello, my name is Dylan Schneider, and I'm going to start my section off by talking about the APIs of Elasticsearch. So Elasticsearch provides two main APIs, the Document API and the Search API. The Document API is used to read, write, and get info about documents that you're going to store inside of Elasticsearch. The Search API actually allows you to search Elasticsearch for the documents that you have stored in there. The Search API takes a big request body, so you can get pretty specific about what you're searching for. Both of these APIs are REST APIs and can be accessed over HTTP with JSON documents. This is pretty cool because this allows you to access Elasticsearch within multiple different programming languages and paradigms. The other cool thing about these REST APIs is they support execution across multiple indices, so they're working concurrently so that they can be as fast as possible. Now I'll actually talk about some routes you can use to hit the document API. As I'm going through these API routes, you'll see that they're all accessed using RESTful verbs such as get, put, delete, post, etc. First, we'll start with the index API. This allows you to insert a JSON document into ElasticSearch into a specific index, making it searchable. As you can see, you'll use the put document in order to add that document to Elasticsearch. The next is the get route, which actually uses the get verb. As you can see, this just retrieves the JSON document based on the ID that you specify in the request. There's also a multi-get API that you can use to retrieve multiple documents. Again, there's a delete API, which just uses the delete verb to delete a document from Elasticsearch, making it unsearchable. There's also a delete by query API where you can mass delete based on a search. Update API, you can use the put or post verbs to modify or update documents. You can also use the update by query API to mass update based on a search. There's also a reindex API where you can just change a document and put it into a different index. As you can see, I've included an example where they just take the Twitter index and reindex it into the new Twitter index. Now, I'll talk a little bit about the extensive search API. One of the first things we have to nail down about the search API is routing. We must understand that when a search request is made, we must hit all shards and all indexes on Elasticsearch. So routing is the mechanism we will use to broadcast the request to all shards. For example, you can use a username as a routing parameter when indexing tweets. So for example, as you can see in the request body of the post request, this request will be routed to any tweet with the user kimchi. This is good for filtering and having routing parameters so you hit relevant indexes and shards at all times. In the previous slides, we talked about how shards can actually have multiple replicas across Elasticsearch. When performing a search request, we must index every shard, including every copy of every shard. Usually this is done just by using round robin to go across the replicas, but we actually have a different process to tell Elasticsearch to do something a little bit different. Something that's called adaptive replica selection is a mechanism implemented into Elasticsearch used to determine the best replica of a shard to use. When going around round robin, we're still determining the best shard to use. However, this way does it a little bit differently. It actually makes a request to each shard and uses a list of parameters to determine the best shard to use in this situation. Now, I'll talk about what uses Elasticsearch and how we can turn this search engine into an actual tool that communicates with other things to make it useful for people in the field. The ELK stack contains Elasticsearch, Logstash, Kibana, and Beats. Beats being data collection, Logstash doing transformations and processing of data, ElasticSearch for everything we've just talked about, like storage and indexing, and Kibana as a UI for visualizations. Now let's talk a little bit more about Elastic Beats. Elastic Beats are lightweight data senders that send information to places very quickly. They're very lightweight as well, so they can be placed everywhere, thousands of places. One great thing they can do is send straight to Logstash, which does data transformation. This makes it quick and easy to get data to Logstash so that it can start doing processing. You can even send it straight to Elasticsearch if you know your data is already formatted in the way that Elasticsearch will take it. These central receivers like Logstash and Elasticsearch can handle thousands of beat senders at the same time. So this is the reason that makes Beats so great and can put them on any type of system to send back to Elasticsearch and Logstash. We also notice that Beats can send all kinds of data. I've included some examples at the bottom, including file beats that just send normal log files, and even heartbeats that just tell the other systems when beats are up. There are tons of other beats you can send as well. Now let's talk about Logstash. Logstash is the server-side data processing pipeline. It is used to collect, transform, and stash your logs here. One great place you can receive data from are beats. These beats will send straight here so you can start your data processing right away. Logstash is really cool because it can ingest data in about any shape, size, or form and start doing transformations on it. After we've done our data transformations, we can then send our data just about anywhere from Logstash. Of course, the favorite of Elastic is straight to ElasticSearch for analysis. Now let's talk about Kibana, the UI used on top of Elasticsearch. The Elastic website describes Kibana as the UI window into Elasticsearch, visualizing everything that Elasticsearch has to hold. Kibana is cool because it allows you to create complex queries into Elasticsearch and display the data in appealing visualizations. These kind of visualizations are anything from basic charts like pie, line, plot, like you learned in basic math class, all the way to elastic maps that allows you to geotag, create custom location data visualizations, to time series where you can plot out events over time. You can even make relationship graphs to compare two different queries of data together. Kibana is also really cool with their visualizations because after you've created them inside Kibana with your Elasticsearch, you can then send them anywhere in just about any format, including PDFs, CSVs, or you can even make it public so that everybody on the internet can see it. Just wanted to show some examples of Kibana charts. So here are some basic charts made by Kibana. As you can see, there's pie graphs, basic plot points, heat maps, and even some flow analyses. This is what I was talking about earlier, how Kibana allows you to geotag your specific events so that you can create elastic maps. These maps use a Google API to determine what on the map to color in and uses your log sources as geotag data points so that it knows where to plot them on the map. This is really cool as you can create some cool visualizations and make your data very appealing to your customers. Here's a quick example of a time series given in Kibana. Here, a date math query is used to determine a range of time to be searched for. Then Kibana will go into Elasticsearch and pull all the events relevant within that timestamp and give you a graph of events over time. As you can see here, application 1 and 4 is graphing the number of requests they can handle per second. As you can see, over the number of seconds, the applications spike in handling more and less requests over time. This is really cool analysis, as you can do some pretty cool monitoring and security tactics with time series. ElasticSearch and the ELK stack are used all over the industry, in big and small companies. One really cool example of ElasticSearch used in the industry is with Slack. Slack used ElasticSearch and the rest of the ELK stack to create the security management of the entire system. Slack uses ElasticSearch to monitor malicious activity happening on the application. As we all know, Slack is a chat application, so you can imagine how many logs of events that they have coming in at any given time. Slack uses the Elastic XPack to send alerts and alarms when malicious data is being transferred, and can actually give helpful insight for security analysts to prevent and stop problems. Users can then use Kibana to visualize their Slack alarms and events to know when and where malicious data is coming in. I've also included a link where you can watch the full talk about how Slack uses the ELK stack in ElasticSearch. Another one of my favorite use cases of the ELK stack in the industry is a cool video game called Overwatch, made by the Blizzard company. Overwatch is one of my favorite games to play, so I thought it would be really cool to include how they use Elasticsearch. Blizzard actually created their own monitoring system called Beam to overwatch Overwatch. They use the ELK stack to actually create the video game and monitor it so that they know it's running at peak performance of all time. So some workflow is when Overwatch launches, Logstash starts ingesting all event logs and starts the monitoring process. So the monitor will actually pull the data sources, including Logstash, periodically. They'll take that data and check it with a bunch of different conditions, which you can see on the right how they've written custom conditions with rules. Then once they've checked their data against these conditions, they'll take actions based on the results. So you can see that since they've created an entire monitoring system for Overwatch, they're able to make sure that the game is running at peak performances at all time. Again, this is a pretty long talk and pretty extensive, so I've included the full link if you want to go and look into more about how the ELK stack is used in Overwatch.